Hi, good evening, everyone. Am I audible?
Yes, ma'am. Sorry.
Okay. Okay, so today is week 8 first session. So in week 8, mostly what we need to cover is binary tree, binary search tree, and magnetic disk, and the different page replacement policies that are there. Other than that, there is also a part on just a little bit about timing complexity of algorithms. So that part I will be discussing later. First, we will start with the part from where more questions will be coming in quiz 2 and NTERM. So that is the binary tree and the magnetic disk part, right? Okay, so let me share my screen. Okay, is it visible to you?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so before we start, what is a tree? Can anyone tell me what's a tree? So before we discuss binary trees, we need to understand what are trees in general, right? So trees are a non-linear data structure, right? You have heard of arrays or lists that you used in Python. Those are all linear data structures. Tree is a non-linear data structure. That means all the nodes in a tree are not present at the same level, right? So the nodes in a tree are present at different levels based on which we have the height of a tree. So you cannot linearly search a tree. Okay. So what is a binary tree? From there we can derive. So in a binary tree, the only specialty is that each node of that tree can have at max 2 children, right? So each node can
At
have 0, 1
most
or 2
two
children.
children.
Yes, at most. They can have 0 children, 1 child, or 2 children. So first we will be starting with the binary tree. So in this week I will be writing some notes. If you want, you can take them with me, or otherwise after the class I'll be sharing these notes on Discourse, so you can take it from there also. Okay. So first thing is binary tree. So from the definition, what can we say? First point in a binary tree. Every node.
Binary tree can have at most two child.
Yes, every node can have at most 2 children.
Yes.
Okay, that's the first point. Now there is a term called arity. Right? What is arity of a node? First of all,
Parity
Number of
kind of
children.
parent.
arity is the number of children that the node has, right?
Yes. Okay.
Number of children. Now, if I ask what is the okay, what is arity of the tree itself?
The node which has maximum number of children.
Right. So the max arity of any node in that tree is the arity of the entire tree, right? So max arity of a node in the tree. Now, for example, let's see what a binary tree looks like. So every node again can have 0, 1 or 2 children, right? So first let us have a root node A. Now root node A has 2 children, B and C. Again, let's say B has 2 children, B
Excuse
and
me, ma'am.
yeah.
Excuse. Actually, I have joined now, and I can't understand anything of this as I have not even read week 8. Can you give me a briefing, very
Yeah,
short?
no, we haven't discussed much. See, in week 8, so there are a few topics that are important. So
Hmm.
one of them is binary tree, then binary search tree, and then we have magnetic disk.
There are
Page.
two terms I have not been understanding because I have never seen them before. Binary tree and arity. You just
Yeah, I'm coming to it. See,
okay.
uh, so today's lecture we are mainly focusing on trees and magnetic disk and page replacement policy. So we'll do numericals from all of that as well. Now, firstly, what is a binary tree? So what is a tree in general? It is a non-linear data structure, right? Like arrays or lists are linear data structure. Tree is non-linear. A graph is also another non-linear data structure example. Now, one
Tree is
type,
acyclic.
yes, acyclic as well. So
What
in
is
a
cyclic?
acyclic means there will be no cycles. Like
Oh,
uh,
acha, means those trees we read in the graph theory of what was that? Math one.
In maths,
That's
in
one.
maths
yes.
we have
So
learned about all this.
Hmm.
right. So trees are all always acyclic. So binary tree is a special type of tree where every node can have 0, 1 or 2. That is at most 2 children each. Okay. So in binary tree we have a term called arity. So the arity of a node refers to the number of children the node has. An arity of an entire binary tree is referred to as the maximum arity of any node in that tree. So if in a tree some node has in case of binary tree it is only possible to have a max arity of 2 only, right? But there are other kinds of trees also who can have more than 2 children. Each node can have maybe n number of children. So in that case, whatever node has the highest number of children in the tree, that is the arity of the tree. Okay, so now we are just doing an example of a binary tree. So A is the root node. A has 2 children, B and C. B has children D and E. And let's say C also has 2 children, F and G. Okay, so A is the root. Now B and C are, we can say, intermediate nodes. And all of these four, D, E, F, G, are
Leaf.
leaf nodes. So A, we call that A or root node is at level 0. Okay, this is level 0, this is level 1, this is level 2. So here if I ask you what is the height of this tree, you will say the height is 2, right? Because the highest number of level is 2. We start with 0, it is 0 based indexing type of. So height of this particular tree in the example is 2. Till now, is it clear for everyone?
Yes, ma'am.
Yes, ma'am. But
Yes, ma'am.
how many types of trees can be there? I mean, is there a finite
Uh,
number?
See, in overall, if you ask, there are a lot of different kinds of trees, but in DBMS, we are only going to study binary trees, and then there are two types of binary trees, like B tree and B plus. I'm sorry, there are two types of trees, I'd rather say. One is B tree and B plus tree. So those two we will be studying, but mostly that will be in week 9 during indexing. We'll discuss. Okay, for now, we are just going to learn about binary tree and binary search tree. Other than that, also there are other types of trees like AVL tree, red black tree, but those are not in our syllabus. So those you can learn about when you go to PDSA maybe. There you will be introduced. Okay.
Ma'am, maximum it can have two childs and minimum zero, right?
Yes. In binary tree, maximum 2, minimum you can have 0 children. Okay, like all of the leaf nodes, they have 0 children. So those are leaves. Now, some properties here we would need to remember is if a tree has, let's say, n nodes, then how many edges can it have?
N minus 1.
N minus 1 edges.
Yes.
Okay. Second, let's say, okay, let's write down the properties of the tree itself. So tree is non-linear, acyclic, and connected. That is, you'll be able to reach every node, right? Now, one more thing is maximum number. Okay, if you don't have a question, please mute yourself.
Ma'am,
Max
what does edge mean here?
edge. These are the edges. Like A to C, there is an edge. C to G, there is an edge.
Okay, ma'am. Thank you.
Yeah. So maximum number of nodes at any level of a binary tree of height h. So how many nodes can be there present at any level, any particular level of a binary tree of height h?
2 power h, ma'am.
Right, 2 power h. So this thing you should remember. This can be asked in numericals, right? Okay. What more? So we can also ask maximum possible nodes in a tree of height h. So how many maximum number of nodes can we have in a tree of height h? So for that, the formula is 2 power h plus 1 minus 1. Okay, so these two formula, these are pretty important for numericals. So for binary tree, just knowing this much information is good enough, because mainly we'll be focusing on a special type of binary tree, which is binary search tree, right? So till now, anyone has any doubt?
Ma'am, this each level must follow the same structure. Like level one has two, B has two childs, so even C should have two. It can't have one.
No, no, no.
Right?
It can have one. It can look like this also. Let's say BC. Here C has two children, D and E, but B doesn't have any children. That is fine.
Okay, so
Okay.
B will be leaf there or intermediate.
Yeah, B is a leaf node.
Okay. Okay.
Whichever node doesn't have a child is a leaf node.
Okay.
Okay. All right. So now let's come to binary search tree. Now I told you about B tree and B plus tree. So just one little difference from what we are learning today and what we'll do in the next week is that now you're getting used to seeing nodes in a tree that can have at max 2 children. After this, when we go to week 9, we'll see that each node can have n number of children. Okay, that is based on the order of the tree. So all of those terminologies will come across in week 9 again. This is just an introduction to trees. Okay. All right, let's start with BST, binary search tree. Again, binary search tree has a lot of characteristics of its own, but the most important characteristic anyone can tell me in a binary search tree?
Ma'am, the elements to the left side of the root node will be smaller than the root node, and the right side elements would be greater than the root node.
Correct. So we can write it down as the value of each node in the left subtree. Okay, let's understand what is subtree. So going back to the previous example, here if A is the root node, all the nodes to the left hand side of A, that is B, E and D, they fall under left subtree, and then this is right subtree, C, F and G. Similarly, if we start from B, the only node in left subtree is D and right subtree is E. So every node, whatever children it has, we can divide it into left and right subtrees. In binary search tree, the rule is here, if A is the root node, then B has to be smaller than A. Right, D has to be smaller than B, and E has to be greater than B but smaller than A. So basically everything to the left hand side of A has to be smaller than A strictly, and everything to the right hand side of A has to be larger than A. Right, then again this relationship continues for every child parent pair. So the value of each node in the left subtree is less.
Why, ma'am? Why? Actually, why will it be?
This is the property of binary search trees. There are different types of binary trees. This is one type. Okay, this rule is not applicable for all different types of trees. It is just a rule for binary search tree. That's how we insert the elements. Okay, it also makes searching a lot easier. So yeah, is less than the root, and for right subtree it is greater than the root. Okay, so anyone can tell me, if I want to search an element in a binary search tree, then what algorithm can help me, or how much time it will take to search an element in a regular ideal binary search tree?
exponential because
N log n, ma'am.
logarithmic.
Is it okay? First, let's understand. So, if I start at the root, right? Okay, let's draw a binary search tree and then do this. Okay, you will help me create it. So let's say we have nodes 18, 56, 1, 24, 32, 13, 8, 42, 74, 36. Let's say these are the nodes. I have to insert these nodes in this exact order in my binary search tree and create the tree. So first root node is 18. 56 will go to which hand side, left or right?
Right hand side, ma'am.
Right hand. Then 1,
Left hand side, ma'am.
left hand side of 18.
18.
24 will go where?
Uh,
Right hand side.
right
So it is
hand side of
greater than
Right hand side of 1.
56. Left hand side.
Left
left
hand
Left hand side of 56.
See, first you will check always with the root. Start with the root. So 24 is greater than root. That means we'll go to right subtree. Right subtree next node is 56. 24 is less than 56. Go to left subtree.
in the left right place.
Yes. First right, then left. So next one, 32 should go where? It is greater than 18.
Right of 24.
24.
Correct. So it is greater than 18, less than 56, but again greater than 24. It will come here. 13 should go where?
Ma'am, right of 1.
1.
Right of 1. Okay, 8.
Left.
Ma'am, left of
Left of
13.
Left of
Left
13.
of 13. See, 8 is compared with 18. It is in left subtree. It is greater than 1, so again in right subtree, but it is less than 13, so in left subtree again. 42 will go where?
Right of 32.
Let's see. So 42 greater than 18, less than 56, greater than 24, greater than 32. So here we'll have 42. 74.
Right of 56.
Right of 56.
Right. So greater than 18, greater than 56. And last 36.
Left of 42.
Okay. Greater than 18, less than 56, greater than 24, greater than 32, less than 42. So this is a binary search tree, right? Now in this, let's say I want to find where is node 32 present. Okay. So here, first step is what? You check the root, compare with root. 18 is less than 32. That means 32 will be in right hand side. So I can easily remove this part of the tree from my search, right? The left subtree, do I need to keep it for the further searches?
No, ma'am.
No, right? So we can discard it. Now we have come to 56.
In binary, there should be sorted list or unsorted list also.
List means the values that you're entering.
Yes, yes. It
No,
should
no,
be
there is
sorted
no order.
order.
You can enter it here. No, see, here I have taken unsorted only, right? I'm creating
Yes.
just random numbers. Okay, so any order you can take. In fact, sorted order is not a good idea. I will tell you just in a bit. First, see, in this step, first step, this half left hand side half of root 18. So left subtree we can discard at this step, right? Now let's come to 56. So 32 is less than 56. So we'll come to the left subtree. Can I discard 74?
Yes.
Okay, now you're at 24. So it is greater than 24. You find it here. Now see, at every step, that is after every comparison, I can discard half of my tree, right? Either the left subtree will be discarded or the right subtree will be discarded at every step. Is that correct?
Yes, ma'am.
So that means to search an element, the best case complexity is log of n. Right? It is like a binary search. In binary search, what do we do? Anyone knows the algorithm for binary search?
Yes, ma'am. We choose a middle element, and if the middle element matches the our wish, what we wanted to search, then we will pick that element. If not, if it is greater than that element, we go to the right side part, and if it is less than, we'll go to the left side part, and we go to the middle element, and we repeat the same thing.
Correct. So binary search takes how much time? Log n, right, to search an element. Whereas linear search takes n time because we have to go through all the elements. But in binary search, again, like you said, at every decision we can discard half the list. So similarly here also, at every comparison you can discard half of the tree for that particular node where you are at.
Ma'am, a small doubt over here.
Hmm.
Since like binary search in a list form, we take n log n because we have to give a sorted list, right?
No, just to search the element. Okay, you are saying the list has to be sorted.
Like for binary search,
Yeah. For binary search, the list has to be sorted. Otherwise, you can't find.
That's what I asked earlier.
No, but
Because
that
now
constraint
the
is not
process
here
we are
for.
doing, now, there's a need of sorted list, right?
No, see. Okay, one second. Let me give an example. Yeah. So here, why in a tree? How do you say we sort elements? Because this is not linear, right? All the elements are at different levels of the tree. So how do you say that we maintain that it is sorted? In what way? How can you sort a tree?
No. Like when we are searching on a tree, then
Yeah,
we have
see,
to.
when you're searching on a tree, when you're at a particular node, you always have two choices only. Okay. Just like in binary search, you have a choice either to go to
Yes.
the left side because you know there are lesser values, or to go to the right side. So similar choice is here also, right? Every step you know that left subtree has lesser elements, right has greater elements. So you get to discard. Similar way as binary search. Okay. But here the insertion of the values don't need to be in a sorted order. Right, you can insert in any order because no matter what happens, we are following the rules, right? For every node, we are making sure that left and right subtrees are having lesser and greater elements only. So this one, in an ideal binary search tree also, the time to find any node is log n, average case, right? Now you said what will happen if we enter the elements in sorted order. So if I have a list like this, 1, 2, 3, 4, 5, so just enter it. It will look like this, right? This is the BST, right? If we enter in sorted order.
Yes, ma'am.
So this is called a skewed tree. Okay, this is not an ideal binary search tree. Ideal binary search tree should have a height of log n. Right, that means we are trying to balance both sides of the root. It is the worst part when all the elements are at one side of the root. That is, here you can see root is 1, but the left subtree of 1 is completely empty and all the nodes are in right subtree. Right, this is the worst case for searching because here there is no binary search happening, right? You cannot do it because there is only one option available to you. So this is you can say it references the same mechanism as linear search. If I want to find 4, I have to go to 1, 2, 3, 4, like this only. It's not like I can discard some part of the tree and minimize some of the search area, right? So
Yes, ma'am.
skewed trees are taking order of n time in average, and an ideal BST will take order of log n time. Okay. Next is okay. So up to this, anyone has any queries on binary tree or BST? All right. Now see, for this week we are not going into a lot of detail because next week is where we will actually see the applications in indexing while we do B tree and B plus tree. But there are some formula related to this. So we will discuss those when we solve the numericals. But I have a formula sheet which I'll share with you on Discourse. Okay. So after the class, I'll share it. You can check it out. But mainly, whatever formulas we have discussed here, that is good enough for these two topics. So let's go to this magnetic disk. Okay, you tell me what is magnetic disk, anyone? Whatever idea you have.
So
Ma'am,
in which
it is
we store.
Yeah, one by one.
Or hard disks.
Hard disk. Okay. What does it do? What is a hard disk used for?
stores our data.
So does main memory. Why do we need hard disk?
It will permanently stay in that system means until you really remove the hard disk. Hard disk was even in older computers means it was hard disk was the main storage one. And
Okay. So can you do any comparisons between main memory and hard disk?
Ma'am,
Ma'am,
hard
RAM
disk.
is non-volatile. Ma'am, RAM is volatile and hard disk is non-volatile.
That's a very important difference, right? So the need for magnetic disk arises, or hard disk, as you said. This is because
ma'am, a small doubt. Then actually magnetic disk means ROM. Exactly.
no, see, ROM means what? Read-only memory. That is, you can't change
Oh,
anything in ROM, right?
okay.
But
Means it is neither ROM nor
no,
RAM.
it's not RAM. We have
Oh,
all seen disks. So
yes.
disks. So
Yes.
yeah, RAM or ROM or RAM, what we will be discussing, random access memory, is your primary memory. So that is, let's make a size comparison. So in most of your laptops, what is the RAM? How much RAM do you have?
18 GB. Ma'am.
Okay, 18
Ma'am,
GB is very
16
good.
GB. Ma'am,
Okay,
16 GB
16
mine.
GB, right? A lot of people have 8 GB also, 4 GB is also there, right? In older models. So RAM has around this much capacity. But when you buy a disk, external hard disk, let's say, how much memory does it have? So on
Ma'am,
Amazon
something.
also you can buy some like 1 TB wala disk, right?
Yes, ma'am.
And it's not even that costly. But if you go to buy a computer with 1 TB of RAM, so we don't have access to that, right? Because it is going to be very, very costly and expensive. So why this happens is because first of all, the need for physical storage, like secondary storage, why it arose is because RAM cannot store a large amount of memory in it, right? RAM has very short memory assigned to it. Like even today, in today's world, you have the memories in GBs, which still seems like a lot, but it's not. That means all the information that you're storing in your computer, like we download a movie or a song, does it get stored in main memory? No, it gets stored in your disk, right? Because this is not something that you are always running on your computer. You're not always watching the same movie on your computer, or it is not a process that always has to run, right? It is something that you are once in a while you're picking up from a folder and you're opening it. So where does it remain stored? Even after you shut down your computer, you turn it back on again, it is still there because it is in the disk, right? If it was in the main memory, it wouldn't be there, because main memory, as you said, is volatile. That means whatever comes into the main memory, it is just there stored temporarily, right? Not permanently. Permanent storage happens in magnetic disk. So physical storage media gives you a lot more storage space. It is inexpensive. So what is one of the drawbacks of physical storage media?
Ma'am, it's slower actually to work with.
Correct. It is slower. It is slower by volumes, right? So what we do is when we want to run something,
Ma'am,
okay.
sorry. What is
Mhm.
meant by volume? Like, is it the speed which they load the data, or which they store the data?
Yeah, I mean that a large volume of data you can store, like a large amount of data you can store
In HDD or in magnetic
in
disk? Like,
magnetic disk or hard disk. Yeah.
yes, yes.
So let's say you have 4 or 5 movies. So they alone will might go up to 20 GB or more than that, right? So you cannot store them in your main memory. That will eat up all the main memory. So it goes into the physical memory. Now, what happens when you want to watch that movie? So you press double click on that movie and it plays. So how it is playing? It is playing in the main memory, because all processes that are running currently are running in main memory only, right? We cannot do processing on hard disk. We only do all kinds of processing on main memory. So CPU parts are what? Main memory, control unit, ALU, right? So this CU, ALU, where do these arithmetic logic operations happen? All of this happens in the main memory, that is RAM. So when you play a movie, it basically takes the frames. That is, it is stored frame by frame by frame, and each of the frames come from the physical storage, that is secondary memory to main memory. That is, every scene that you are watching a tremendous number of page transfers are happening or frame transfers are happening, right, between your physical memory and your main memory. So everything is brought from the disk to the main memory, and then once it is done, it is again brought back to the disk, right? So when you are rewinding a movie, let's say, you're again calling those old blocks again from the hard disk. So main memory is the faster option. It is very fast, it is very expensive, and it does not obviously have a lot of storage because it is expensive. There are also parts of RAM like SRAM, DRAM, right? SRAM is used in your cache. So we have cache memory. What does cache memory do? It is even it's sort of like a hierarchy, right? The secondary physical storage, which is the slowest, then we have RAM, which is faster, then we have cache, which is even faster. Because what is the work of cache? It keeps track of what all processes you are running the most frequently, right? Those are stored in the cache. Then we have levels of cache, L1 cache, L2 cache. We won't go into that much details. So cache memory maintains the most frequently accessed records, you can say. And main memory, whatever processes are currently happening are always happening in main memory, right? So now let's discuss magnetic disk itself. The structure we will know, and we will know how it works, right? How things are stored on there. So before we do that, let me show you this picture. So this is a magnetic disk. So there are a lot of components to it. You can see that these platters, right? These are called platters. Each of these circular disks, you can see, they're platters. This is your ARM assembly, right? That is written here. This thing that is, you can see it is holding the disk or the platter. This is your read-write head. Now the cylindrical rod in the middle, this is called the spindle. So what happens? These disks rotate around this spindle, right? That's their axis. So they rotate, but the read-write head is fixed. Fixed means it won't rotate along with it, but it can move laterally, right? That is, it can move in this direction or this direction. Okay, so these are some of the different parts of a magnetic disk, but we need to take a closer look at each of the platters. So what does each of these disks contain? So each disk has how many surface?
Two surface.
Two surface. This is the top surface and the bottom surface. You can see two parts of the read-write head, right? And these two move together laterally. So let me draw it. Not a very good drawing, but I hope you will understand. So if this is our, let's say, the top view of one of the disks, right? So each of the surface has these concentric circles like this. This is the spindle. Now each of these surfaces, they are called tracks. Each of these concentric circles, they are called tracks. Okay, now let's divide it like this. This part is called a sector. Sector is the smallest unit of storage on a surface of a platter, right? So a surface of a platter has tracks and it has sectors. Now see, all of these sectors that I've drawn, they're basically on a track, they're of the same size. Okay, my diagram doesn't show that, but in a particular track, all the sectors are of the same size. Okay, now here we have that read-write head, which, so this arm is what moves, right? So this can move either to the innermost circle or to the outermost, that is, it can move throughout the disk. So here, how it reads the data is, it has to first access the correct track on which my desired data is, and then it has to access the correct sector on that track. So the first point is the read-write head is fixed, but it can move along the surface like this, just laterally. the disks rotate. Okay. Now here in magnetic disks mainly we'll be learning a lot of numericals. So there are a lot of formula associated with it, right? And a lot of terms. So the first thing is seek time. So what is seek time? First, when I know that I need to fetch some data from the magnetic disk, the first thing I will know is in which track is the data stored, right? So seek time is the time. See, we are doing a very overview of it. Okay, we are not going into the internal mechanisms. We are just teaching you how to just understand the basic working of a magnetic disk. Okay, of course, a lot more is involved in this. Now, first seek time is the time required to position the read-write head onto the
Desired disk.
desired track to find the correct track. Okay. Now, there is one more term, rotational latency. What is rotational latency? Now we have found the track. Next, what unit of storage should we check? Sector, right? Those are the only two things we need to work with, tracks and sectors. So once I have found the track, now I'll find the sector on it, that on which particular sector my data is present. So it is the same thing, time required to position the read-write head onto the, so I will just write that same thing, but for sector. Okay, so position the read-write head on the correct sector. But when we actually work with these terminologies, we won't be using rotational latency, we'll be using average rotational latency. So average rotational latency is what? It is half into 1 complete disk rotation time. That's average rotational latency. That is the average time to find any sector on a particular track. Okay. Now, another important formula is how to find the total number of sectors on a surface, or we can say on a platter. Okay. Or even if you want, you can say that we can find the total number of sectors on all platters. That is, in this diagram you can see these are all the different platters. So what is the total number of sectors including every platter? Total number of sectors. So each platter has how many surfaces?
2.
So 2 into number of platters. Now in each surface there are tracks present, right? So we will multiply with number of tracks per surface. This 2 takes care of the 2 surfaces, right? So number of tracks per surface, again we need number of sectors. So there are sectors present per track. So number of sectors per track. This is the formula to find total number of sectors. Okay, a lot of numericals have come from here. These two formula are important. Alright, now one more thing is, now we found the number of sectors, but what is the disk capacity? That is, how much storage does the disk have? So you know what is the smallest unit of storage, that is sector. Now we know how many sectors are there. So what should be disk capacity?
Ma'am, sorry for interrupting. Could you once again repeat number of sectors part?
Yeah, so number of sectors, we are trying to find how many sectors are there in the entire hard disk. Right, so we saw that there are multiple platters and each platter has 2 surfaces. So 2 into number of platters. Then on each surface we have different number of tracks, right? So number of tracks per surface has to be multiplied. Then on each track we have a certain number of sectors present. So number of sectors per track. So all of this together will give you the total number of sectors in the entire hard disk unit. Right?
Ma'am, a small doubt over here about number of sectors per track. Since sector is like the area between two tracks only, right?
Hmm.
Like, then are we counting tracks twice? Because
No. See, number of tracks per surface. Let's say in one surface there are 5 tracks. Okay. Then again, each track has a certain number of sectors. So for every track, what is that number of sectors? So if there are, let's say, 6 sectors on each of the tracks, so total number of sectors is 5 into 6, 30. Right now, this many sectors on just one surface. Then again multiplied by 2 because there are 2 surfaces for each platter. So that is total number of sectors on a particular platter. Multiply by number of platters. That is total number of platters. Then you get total number of sectors combined in all the platters. So my question is that when we talk about disk capacity, that is how much the entire hard disk unit can store. So you know the smallest uh, storage unit is sector. You know how many of those sectors you have. So what is the disk capacity then?
Number of sectors?
The number of sectors on a disk.
Number of sectors is not the capacity, right? It is a numerical value that this many sectors are present. So number of sectors into
Ma'am, multiplied by capacity of a sector, one sector.
of one sector, correct. So this is the disk capacity. Number of sectors into capacity of one sector. So you can just multiply and find out how much you can store in this disk.
Ma'am, in number of sector, you are multiplying 2, but you are also using the number of platters.
Yeah, platter is the entire, like one such circular disc. This is a platter. Each platter has 2 surfaces, right? Top surface and bottom surface.
Yes, ma'am, but you are already using 2, no?
Yeah, that 2 is for the different surfaces, but we also have to take the number of platters into account. So each platter has 2 surfaces. There are 3 different platters, if I say. So total number of surface will be what? 6.
Okay, ma'am.
Perfect. Now, one more thing before we go to the numericals is if you don't know these conversions, please just keep them in mind. Few conversions.
ma'am, over here, capacity of one sector, how do we find that?
That will be given in the question.
Okay.
Okay. So conversion first, let's say what is 10 2 to the power 10 bytes means 1 KB. Right, 1 kilobyte is 2 power 10 bytes. What is 2 power 20 bytes? 1 MB.
Megabyte MB.
2 power 30 bytes?
1 gigabyte.
1 GB. Right. So these 3 conversions, and for time also 1 second is how many milliseconds?
1000
10
milliseconds.
power minus. Oh yeah, 10 power.
10 power 3 milliseconds, right? 1 millisecond is 10 power minus 3
Yes.
seconds.
Yes.
Okay. So 1 second is how many microseconds?
10 power 6.
Microseconds. And nanoseconds?
10 power
10 power
9.
9.
Okay, so just remember these few conversions for the numericals. Okay, one more term I forgot is access time. So access time is equal to seek time plus average rotational latency. That is, this is the total time required to access the desired sector. Right, first you have to locate the track, that is in seek time, then you have to locate the sector. So it is a sum of these two. Now this one I think you can figure out. What is transfer rate? So transfer rate means what? We are transferring the data, right, from physical to main memory. So what is that transfer rate? So we can say bytes
Per second, ma'am?
Yeah, you can give per second, per millisecond. That depends on the question it will ask. Okay, but what is the general formula is number of bytes on one track by time required for one full rotation. Right, because in one full rotation you can cover a full track because these are concentric circles, right? So you can cover a full track in one full rotation, and whatever number of bytes are stored in that track in form of sectors, so divided by that, that will be your transfer rate. That is, this many bytes can be transferred in this much time. So in one complete rotation, how many bytes you can transfer? That's your transfer rate. Okay, but there is a different term called transfer time. So what should this be? Whatever is your file size by the transfer rate. At this rate, I can transfer the data from physical to main memory. So what will be the transfer time for, let's say, a file of 100 KB? So if the transfer rate is 50 KB per millisecond, and the file size is given as 1000 KB, so you have to just divide the file size by the transfer rate, and that is the
It's
transfer
like
time.
speed, time, and distance, something.
Yeah, it's like speed, time, distance, exactly. Okay, so these are the different formula you should keep in mind. So I hope all the formula is clear to everyone. For now, you can take a screenshot before we do the question, so you can refer to it. But just learn these by heart before the exam.
Ma'am, these notes won't be uploaded?
Yeah, I will share it to you on Discourse. Okay, I have it on Drive.
Okay, thank you.
Ma'am, what is average RT? What is the full form of RT?
Average rotational latency. So we don't use the word rotational latency, we take average of it. That is half of one complete rotation.
Okay.
Okay. So whenever in any question you are asked to find rotational latency, you'll always find the average rotational latency. Okay. So if you can remember all this, good. Otherwise, just take a screenshot and we'll start with the questions.
Ma'am, a small query. Like in exam, would we be given such formulas like in stats we had?
Formulas won't be given. So
Okay.
these things you have to remember. Okay, but see, these are not something you have to memorize. I mean, if you understand the terms, you will be able to derive them. So I'll just do some PYQ type questions only from here, so you can understand what type of question will come. Okay, should we start with the questions? So numericals on magnetic disk. So first one, what I'll do is I'll give you the question. I'll give you around 2-3 minutes to solve. Then I'll solve it. Okay.
Ma'am, once could you go to the formula sheet?
Yeah.
Yeah. Okay. Like taking a screenshot.
Hmm.
Yeah, could you go down a bit? Done, ma'am.
Okay, and this is the transfer time. Okay, so first question, let's see. Consider a magnetic disk with 8 platters, 2 surfaces per platter, 1024 tracks per surface, and 2048 sectors per track, and sector can store, let's say, 512 bytes. The disk rotates at 6000 RPM. The question is, what is the capacity of the disk? And your answer should be in gigabytes. Okay, so please solve this question. Just take 2 minutes, see the formula and solve this. If anyone has the answer, you can tell me. Did anyone get it? Okay, first You can tell me which formula will we need to use here.
Number of sectors might be useful.
So we are asked the disk capacity, right? So the disk capacity is what number of sectors into capacity of one sector.
Yes.
Capacity of one sector is given 512 bytes. So you just need to find the number of sectors. So let's find out number of sectors, that is 2, that is for 2 surfaces per platter. How many platters? 8. How many tracks per surface? 1024. 2048 sectors per track. Right, just let's convert them into powers of 2. So 2 power 1, 2 power 3, 2 power 10, 2 power 11. This is equal to 2 power 25. So this many sectors are there. Now we need disk capacity. Disk capacity is number of sectors into capacity of one sector. So you have 2 power 25 sectors. Capacity of one sector is 512 byte. 512 byte, how much is it in power of 2s?
2 power 9.
2 power 9. So this together is 2 power 34 bytes. How much is that in GB? 2 power 30 into 2 power 4 bytes is 2 power 30 byte means what in the conversion?
3 GB. Sorry.
2 power 30 means 1 GB.
Yes, ma'am. 1 GB.
So 2 power 30 bytes into 2 power 4. So that is 2 power 30 will convert to 1 GB
16.
into 2 power 4, that is 16. So it is total of 16 GBs. This is the disk capacity.
Ma'am, can you please repeat how this number of sectors is coming?
Yeah, see, this is the formula that we just discussed here, right? Total number of sectors. So here we have these different platters, right? These disks are called platters. Each platter has 2 surface, top surface, bottom surface. So in our formula we have 2 into number of platters, that is 2 surfaces per platter. So 2 into number of platters into number of tracks per surface. So on both surfaces there are tracks present, these concentric circles. So number of tracks per surface. Now each track has number of sectors on it, right? So into number of sectors per track. This is the total number of sectors in the magnetic disk. So just use this formula in this question. So the question is asking for disk capacity, which takes number of sectors into capacity of one sector. Sector is the smallest unit of storage, right? So this total thing will give you disk capacity. So number of sectors first you find out. Here in the question it is given there are 8 platters. So 8, 2 surfaces per platter. So 2 into 8. Okay, that is total number of surfaces. Now how many tracks? In total 1024 tracks per surface. So total number of surfaces into 1024. Total number of tracks. Now 2048 tracks per track, sectors per track. So total number of tracks into 2048, that is total number of sectors. Now just you arrange them into powers of 2. So you get 2 power 25 sectors. Okay.
Yes, ma'am.
Now
Yeah.
disk capacity is, we have the number of sectors and in question it is already given sector can store 512 byte each. So this into 512, now you just do the conversion from byte to gigabyte. Right, 2 power 34 means 2 power 30 bytes is 1 GB. So remaining is 2 power 4, 16 GB.
Ma'am, is it BYTE or BIT? Like byte?
No, byte.
Okay.
Okay. Is it clear for everyone, this
Yes,
question?
ma'am.
Yes.
Yes, ma'am.
Okay, so one more question that we can ask from here is, what is the maximum number of bits required? Okay, not, let's say not maximum, this is wrong. minimum number of bits required to address all the sectors uniquely. From this same question, if I ask this part question, that how many bits do I need to address all 2 power 25 sectors uniquely? So what should be the answer? This many sectors you have.
Is it multiply by 8, ma'am?
No. Why multiply by 8?
Like this capacity is 16 GB and I don't remember
No,
this quite.
see, this has nothing to do with capacity. Okay, this is just addressing. Like if I want to reach a particular sector, if I want to address the sector to some unique address, every sector if I assign a unique address, then how many bits will I require to do that? In case of this minimum number of bits, if I have 2 power 25 sectors. Okay, see,
25.
25, correct. So what is the logic behind that? If I have 2 bits, 0 and 1, how many combinations can I form? Unique combinations?
2, ma'am. Sorry, only yeah, 2, ma'am. 0, 1,
4,
and
2,
0.
0, 1,
4.
and 1, 0.
0,
So
0, 0, 1, 1, 0, and 1, 1, 4.
correct, 4. I haven't said you can't repeat the bits. I have said I have 2 bits, 0 and 1. Now you can use them any way you want. So I can have 0, 0. That is one combination. I can have 0, 1, or I can have 1, 0, or I can have 1, 1. So 4 unique combinations are possible from 2 bits. From 3 bits, how many unique combinations we can get?
8, ma'am.
8. So just 2 power 2, 2 power 3 like this.
2 to the power
No, 2 to the
n.
power n.
So 2 to the power 3.
Right. So if I have n bits, then I can get how many unique combinations? 2 power n. So similarly, if I have 2 power 25 sectors, can I say that 25 bits can have 2 power 25 unique combinations? Right. Each of these
Yes.
combinations are unique, right? For 8 bits, I have combinations like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and continue. Right. So if you have 25 bits, you can easily uniquely address 2 power 25 sectors.
Ma'am, so 25 bits are there to address 2 power 25
Yes. 2
sectors.
power 25 number of sectors.
Got it.
If we want to uniquely address all of them, we need at least 25 bits. Okay, so this one is over. Now let's go for the next question. Okay, just do this carefully. Look at the data that is given. So given the rotational speed of a disk is 6000 RPM. Okay. Consider the seek time is 3 milliseconds. What is the rotational latency? So what did I say? Whenever we ask rotational latency, you have to give the average one. Okay, you have the formula. Try to solve this. RPM means what?
Rotations per minute.
Right, so per minute. Right. Now solve this question. What is the formula for average rotational latency?
Half
into one complete disk rotation.
Time for one complete rotation. Correct. So just find out that time, one complete rotation, how much time it will take. And remember the answer should be in milliseconds because here the data is given in milliseconds. Got it, anyone? Should I solve? Okay. See, first average rotational latency formula is half into 1.
Ma'am, 5 millisecond is the answer.
Yes, 5 milliseconds. Good. So 1 complete rotation. So here I have the rotational speed given to me 6000 RPM. That means 6000 rotations in 1 minute or 60 seconds. 1 second means how many milliseconds?
10 power 3, ma'am.
10.
So 60 seconds means 60 into 10 power 3 milliseconds. So 6000 rotations in this many milliseconds. So 1 rotation 60 into 10 power 3 by 6000. So I can write 60 into 10 power 2. Okay, so 10 is remaining. So 1 rotation in 10 milliseconds. So average rotational latency is half of that. So half into 10, 5 milliseconds. Anyone who did not understand this?
Ma'am, what is 3 here? Like,
Seek
we
time is
doesn't use.
just, yeah, it is just given to distract you. Like if you don't know the formula, you might use it. Okay, it's not required to find it out. This is clear for everyone?
Yes, ma'am.
Okay. So in this question, if I had asked what is the access time?
Ma'am, 8, ma'am. 5 plus 3.
So seek time plus rotational latency 3 plus 5, right? This part questions can come like this. Okay, let's do a bit of a tougher question now. So consider you have a file in your hard disk of size 1000 KB. Seek time of hard disk read head is 3 milliseconds and rotational speed is 30,000 RPM. The disk has 200 sectors per track. Okay. Question is, what is the transfer rate of your hard disk in KB per millisecond? Oh, also here, let's say one sector can carry 512 bytes. Okay, please try to solve this. See all the information that is given to you. Everything you require is here. You need
Ma'am,
to
could you read the first line once? Consider you have a file in your, what is that, ma'am?
hard disk, HD.
Okay.
Hard disk of size 1000 KB. So first, what is the question that is being asked? That what is transfer rate? Right. So transfer, So transfer rate. First, you need to find out what is the formula for transfer rate that you already have. It is
File
number of
size by time required for
No.
one rotation.
No, that is transfer time is file size by transfer rate.
Yes.
Okay, transfer rate is number of bytes per track by time required for one full rotation. So first you need to find out the components of this fraction in your formula. What is the number of bytes per track? What is the time required for one full rotation? So we need to find what transfer time, number of bytes per track by time for one full rotation. So anyone found this number of bytes per track? Sectors per track is already given. How to find out? Tell me. Number of bytes per track. Number of byte means how much I can store, how much memory I can store in one track. So what is the smallest unit of storage on a track? Sector. That means number of sector per track into capacity of one sector. So how many sectors per track? 200. Capacity of one sector is 512 bytes. So that many bytes per track. Is this clear?
Ma'am, once could you repeat this?
See, transfer time, what is the first part? We need to find out number of bytes per track. That is how much memory stored in one track. So memory in a particular track is stored in the form of sectors. So in one track, how many sectors do I have? In the question it's given.
200 sectors per track.
So 200 sectors per track, what is the capacity of each sector? 512. So how much memory per track? How many number of bytes per track?
200 into 512.
200 into 512. Okay. But see in the answer, we wanted in KB per millisecond. This is in bytes. Okay.
200 KB per second?
Convert it.
So let's
1024 KB is equal to 1024 bytes is equal to 1 KB.
Right. So let's first here simplify this. So 200 into 512 bytes, that is 102400 bytes, right? Now here I can write 100 into 1024 bytes. So 1024 byte is, like you said, 1 KB. So this is 100 KB.
Yes.
So 100 KB is stored per track. Now second part of the fraction is time for one full rotation. So this is just like the previous question. Here again RPM is given to you. So 30,000 rotation in 60 into 10 to the power 3 milliseconds. One rotation in
16 to 10 to the power 3 by 30,000.
13 to 10 to the power 3. So this is 2 milliseconds. So now what is transfer rate? Just put these in the form of the fraction. So 100 KB
100
by 2 milliseconds. This is 50 KB per millisecond.
50 KB per meter second.
Millisecond. Okay, so this is the answer to the primary question, what is transfer rate? Is this clear for everyone?
Ma'am, how did you convert 200 into
See, first we had 200 sectors, 512 bytes per sector, right? So 200 into 512 gives us 102400, this many bytes. 1 KB is how many bytes? 1024 bytes. Okay, 1 KB is equal to 1024 bytes. So 102400 bytes, I just wrote that in the form of this 100 into 1024 bytes I can write. So 1024 bytes now converts to 1 KB. So 1 KB into 100 is 100 KB.
Okay, ma'am. Ma'am, I'm yet confused about the number of bytes per track.
Number of bytes per track. See, how many sectors per track?
There
200.
are sectors. Yes, ma'am.
Each sector can have how many bytes? 512. So 200 into 512 is total number of bytes per track.
Okay. Okay. I get it, ma'am. Okay.
See, if this is part of a track, okay, these are the sectors. Okay, so the sectors contain the information. So how many sectors are there? How much information one sector can have? The multiplication is the product. How much bytes per track is there?
Yes, ma'am. Yeah, got it. Got it.
Okay, and I hope this calculation is now clear to you, just how to find out.
Yes, ma'am. That's unit maths, right?
Yeah. So transfer rate, we know. Now, what is the question asking? Transfer rate of your hard disk in this much. Okay. Now from here we can ask another question also. What is that? We can ask what is transfer time. What is the size of your file according to question?
1000 kb.
1000 kb.
So what is the formula for transfer time? File size
File size
by transfer rate.
transfer rate.
So you have 1000 kb by 50 kb per millisecond. So this is
200.
200. Not 200, it is 20.
20. Ma'am,
20 milliseconds.
How 1000 kb has come? Once could you show that?
It is given in the question. File size is 1000 kb.
Okay.
Transfer time formula is file size by transfer rate.
And then what is the capacity which we calculate with the number of sectors?
That is disk capacity. That is how much the total capacity of the disk is. This is one file you are storing in the disk.
Okay. That's the total size of the disk, and we here given that one small
one
part.
File size. Yeah.
Got it.
Okay, so 20 milliseconds is your transfer time here. Now, what is the access time here? See the question. Is anything mentioned?
Yes, ma'am. Seek time is given, and we can find the rotation average rotational time.
Latency.
We can sum that.
So, average rotational latency is how much?
Half times
one complete rotation. So, one complete rotation takes how much time?
2 milliseconds. So
2 milliseconds. So, half into 2. 1 millisecond, that's your average rotational latency. Seek time is given as 3.
3 plus 1.
So 4 milliseconds is access time.
Yes, ma'am.
Okay, so these sums are very easy to do. You just have to remember the formula, that's it. Okay. What else we can ask? Just let me check once. Okay, let's ask another part question. How many sectors required to store the file? This is again based on size only. So what is the file size? 1000 kb. KB to byte conversion, what do I multiply with? 1 KB is how many bytes?
2 to power 10.
1024, right? So 1000 KB is 1000 into 1024. That many bytes. How much can one sector store? 512. So this is the total number of bytes present in the file. Each sector can store 512 bytes. So how many sectors we need to store this entire file is 2000 sectors. Is this clear?
Ma'am, how did you get 1024?
1024 bytes means 1 kilobyte. Okay, the file was 1000 KB.
You have converting it to bytes, right?
Byte, yeah.
Single byte.
Otherwise, I can't divide, right?
Oh, okay, got it. So, yeah.
Okay. Or if you don't want to do that, just convert this one into kilobyte. That also works. So 512 byte means half kilobyte. So that will also give you 2000 sectors. So many different part questions can come, but all are very simple only. Are all the problems clear to you, whatever we have discussed? Anyone has a doubt? Yes, these are important for end term and all, right? Okay. So last topic we will be discussing today is page replacement policy.
Ma'am, small doubt. If we are asked the number of sectors in a disk, then from capacity of disk we can just multiply.
Capacity of disk. If you want to find out how many sectors in a disk, then you must know that how much each sector can store. So that will be capacity of disk by how much each sector can store. That is the number of disks. number of sectors. I'm sorry.
Okay, got it, ma'am. Yeah, you can continue.
Okay. So page replacement policy. Now we will be discussing two methods, but there are other methods also. Okay. So first of all, let's understand what is page replacement policy. Anyone has any idea? So page replacement is that same example I will take, which I took when we were understanding why we need secondary memory, right? So I said that let's say you try to watch a movie on your laptop. So where is the movie stored? Again, secondary media, right? Secondary storage media. Now from the hard disk, the movie has to come into the main memory, but the main memory doesn't have that much space that you can get the entire movie and pick it up at once from the disk and transfer it to main memory, right? Main memory needs to run other processes also. So we cannot occupy the entire main memory. We will bring the movie frame by frame from physical storage to main memory. So for example, let's say this is my main memory. Let's say I have the frame stored like this 1, 2, 3, 4, 5, 6, 7, and on. So these are the frames of the movie. Okay. These have to come in this order. First this frame, then this frame, like this. Now this is our main memory. This is hard disk drive. This is main memory. Let's say main memory buffer has only, buffer means the workstation where the processing happens. It has only 3 frames, 3 page frames it has, or 3 slots it has. Okay, so at max, 3 frames can be in main memory at once, not more than that. So first let's take this frame. First frame will come first slot. So now 1 has been entered. So what happens is when we try to get a frame from the physical storage to the main memory, we check if it is already present in the main memory. Okay. If it is already present, then it's called a hit. That means we don't have to bring it again. It is already there. But if it is not present in these 3 slots, that means it is a miss. So we have to bring it. We have to transfer it from hard disk to main memory. So this 1, it was a hit or a miss?
A miss, ma'am.
It was a miss. Now next is 2. This is also a miss, not present. So we enter it. Next 3 is also a miss. So enter 3. Next frame is 4. This is hit or miss?
Miss, ma'am.
Miss, because none of the slots are empty and none of them contain 4. So now comes the notion of replacement, right? Because I need to show the next frame to you. So let's say these 3 frames cover the first 30 seconds of the movie. Now you want to move on to the next 30 seconds. So page frame 4 needs to come. Now this is where we have different types of replacement policies. So we have something called least recently used replacement policy, LRU, or we have MRU, that is most recently used. Now there are other policies like optimal also, which we are not going to discuss in our syllabus, but it is there. Okay, so we just need to learn LRU and MRU. So let's start with LRU, that is least recently.
Ma'am, I just don't understand this part.
Yeah, which part? Like why we need this page replacement policy?
When you replace 1, it missed. When you replace 2, it missed. Why it missed?
Yeah, I'll tell you 1 second. Wait. Least recently used or LRU. Okay. See, initially I said the slots were empty, right? In main memory, we have 3 empty slots in the buffer. This is where the page frames need to come from hard disk. But every time we want to transfer a page frame from hard disk to main memory, we try to check whether main memory already has that page frame present. If it already has a copy of it, then we don't need to do another transfer, right? Because that is just waste of time. It is already present, then you keep it there. So here, initially when all slots are empty, I want to bring in the first page frame 1. Is it already present in main memory?
No.
So it is a miss. Whatever is not present and we have to transfer is a miss. So first 1 comes, then 2 is also not present, so it is also a miss. It is stored above 1. Then 3 is also a miss, it is stored here. Now when 4 wants to come, it is a miss, but there are no other slots to enter it. Now which page will I, or which page frame will I replace to store 4?
Like 1, 2 and 3 was not here, that's why we replace it.
Yeah. Okay, I will give you an example. You will understand. See, if I want to bring page frame 4 next, okay, there is no way to bring it other than replacing one of the page frames already present in the buffer, because the buffer has only 3 slots. But instead of 4 here, if I had 1 again, or let's say I'll just give you a sequence of page frames that we want to bring. So if it was 1, 2, 3, and then 1 again. So first this one entered here, 2 entered here, 3 entered here. Now if I want to access page frame 1 again, will it be a hit or a miss?
Hit.
Because 1 is already present.
Yes.
Right. So in case of LRU, what happens? Least recently used. So that name is the clue. Whichever page frame has been least recently used, that means it is the oldest page frame in the buffer, that one will be replaced. So here if I want to bring 4 when 1, 2, 3 are present, now which one should be replaced? Which page frame came first?
1.
1.
One.
So 1 is the oldest one or least recently used one. So 1 will be replaced and it will look like this. 2, 3, 4.
4.
Okay. Now here, if I say now I want to access page frame 2, it is a hit, it is already present. But now page frame 2 is the most recently used, so you have to change the order. So it is now 3, 4, 2. So a sequence of page frames will be given to you, that is, this is the order in which I want to.
Ma'am,
Yeah.
actually this is like search history.
Yes. This algorithm is used in a lot of places, okay.
Yes.
Now, in exam, what will be done is, we will give you this is the sequence in which I want the page frames to come into the buffer. Okay, let's take an example. These are the page frames. Let's say 3, 4, 1, 4, 2, 3, 1, 4, 2, 3. I want the page frames to come into the main memory buffer in this order. So if my main memory buffer has only 3 slots, so what is the first page frame? 3. Hit or miss?
Miss.
Miss. So 3 comes here. This is a miss. Next 4. Hit or miss?
Miss.
Miss.
Whenever there are empty slots, it's always going to be miss, right? Unless the page frame is already present. So 4 comes here. It is also a miss. 1.
Miss.
Miss. So 3, 4, 1. Which is the most recently used one and which is the least recently used one?
1
Least is
1 and 3 is the least recently.
3 is the least, right? 3 came first. It is the least recently used. 1 is the most recently used. So these are all 3 misses. Next, I want to bring 4. Hit or miss?
Hit.
Now, where should 4 go?
To the top, ma'am.
To the top, because 4 is now the most recently used. Other slots will maintain their position. So first 1, then 3. This is a hit because 4 was already there. Next is 2. This is what?
Miss.
miss.
Miss, because 2 is not present. So which one will be replaced?
3.
3.
Least recently used. That is 3. So rest of them will maintain their positions. So first 1, then 4, then 2 comes as the most recently used. Okay, this is a miss. 3.
Hit.
Tell me the order from top to bottom.
2,
4,
4,
2
1.
and 3.
No, we are entering 3.
2, 4,
4,
3.
2 and
3, 4, 1.
Sorry. 3, 2, 4, ma'am.
Which one will be replaced?
1.
1. So there is no 1 here. What are the other frames that will be present? 4 and 2.
Yes, ma'am.
So top to bottom, the order should be 3, 2,
3, 2, 4.
4.
4. Just remove this and drag these 2 down. That's it. So this is also a miss. This one, it is hit or miss.
Miss.
Now tell me the order.
1,
1, 3,
3, 2.
1, 3, 2. This is also miss. Next is 4.
4, 1, 3.
1 was already there
4,
in
1,
the
3.
4 is not in the last list.
See, 4
4
is
1 3.
not in 1, 3, 2. Okay.
Yes, 4
Something
1
has to be
3.
replaced. 2 has to be replaced, so it is 4, 1, 3. This is also miss. 2.
2 4 1.
Also miss.
2 4 1.
Okay. 2, 4, 1, 3.
3 2 4. 3 2 4.
That is 3, 2, 4. So how many hits are there? How many misses are there?
1 it is here and all other misses.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. We have 9 misses. In total, we are trying to reference 10 page frames. We have 1 hit, 9 miss. So now from here, we can ask you what is the hit ratio? That is how many hits by total number of page frames that you reference.
1 by
So
10.
1 by 10.
10 by 10.
Right. The miss is just the opposite, 9 by 10. This is LRU policy. That is, we always replace the one which is least recently used. Is this clear for everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So if I give you a page reference, let's say a string like this, so you can figure out how many hit, how many miss will be there if the
Yes,
number of
ma'am.
slots are given. See, every buffer slot won't have just 3 slots. There might be 4 slots present. Okay, that will be mentioned in the question.
Ma'am, buffer slot is main memory.
Main memory buffer where the processing is going to happen.
Okay.
Okay, now if you understand this, then MRU will become very easy. So most recently used. This is just the opposite. So working with the same series, let's note it down again. So it is 3 4 1 4 2 3 1 4 2 3. Okay, so you will just tell me which one is hit, which is miss, and what should be the pattern. First 3, hit or miss?
3
Yes.
miss.
Miss. As long as it is not present and empty, it is always a miss. So then 3 and 4.
4 miss.
This is 1 4
1 4 3 miss.
Next, this 4.
Hit.
This is a hit. Okay. So now what is the most recently used one?
1.
4.
1
4.
4
Which one is called last? 4.
4
This goes to the top. Then 1.
4
Then
1 3.
this is a hit. Now you have 2. So which one will you replace? What is the most recently used one?
4.
So 4 will be replaced. In
2
that
1
case,
3.
2
2
will
4 1.
2 1 3. This is most recently used. So most recent page frame is 4. That is replaced. Earlier we would have replaced 3, least recently used. Now 4 is removed. In that place 2 comes. This is also a miss. Now you have 3. Hit
Excuse
or
me,
miss?
ma'am. In the third block, like 1 4 3, we must replace the most recently used, and that is 1.
Yes.
And in place of that, we should have put 4. So how come 4 1 3 is there?
Because 4 was not a miss. We are not replacing. We are just changing the slots.
Okay.
We are trying to keep a track of where the most recently one is stored. Look, you can insert in a different order also if you want. Okay, like here I am maintaining it such that the top block is always the most recently used one. You can also store it like the bottom block will be the most recently used one. Like if you store like this, first 3, then 3 4, then 3 4 1, like whatever is there in the data, you can store it like this also. Okay, so that is up to you. Just make
Okay,
sure you know which slot contains the most recently used one.
But ma'am, if it missed, we will remove the oldest one. But if it hit, we will remove the earliest one.
No, if it is miss,
Yes.
okay, only then replacement happens. Okay, if you don't have the block, if you don't have the frame that you want, then only you have to replace. If it is already present, then you just change the order. Like here, 1 4 3, right? Next frame was 4. 4 is already present in the second slot, but now it has been accessed, so it became the most recently used block. so it came to top, and then 1 and then 3. But when I tried to look for 2, 2 was not present, so now 2 is a miss. So
Then
now we
like
have to replace.
then it should be 241. Why 213?
Because here, what is the name of the policy? Most recently used. So the most recently used block is replaced.
Okay.
4 is most recently used. Remove it. Place 2 in front of it, in place of it. Okay, and rest of the blocks remain same. So now you have 2, 1, 3. Next, if I have 3, it is a hit or a miss.
A hit,
It
ma'am.
will hit 3, 2,
What
1.
is the order?
3, 2, 1.
2, 1. Correct. This is the hit. This 1 is what?
1, 3, 2.
132.
1, 3, 2.
Hit. So 1 became most recently used, then 3, then 2.
2.
4 is what?
Miss.
Miss.
2. Miss.
So it
Miss.
will be replaced with 1.
432.
4, 3, 2. Next we have 2.
243. It's a hit.
It's a hit. So 2, 4, 3.
3.
This is hit.
Hit.
Last one 3.
It's a
Also
hit.
Hit 3,
324.
4, 2, 4.
3, 2, 4. Good.
Yes.
So now how many hits we have?
4, 5.
We have 5 hits. And how many misses we have?
5.
Also 5. What is the hit ratio?
5 by 10.
0.5, 50%. Ma'am, a small doubt over here. Like when we are removing the most recently used one, like it is a loss only, right? Like if the person is
No, in my case, I have maintained that my top block on the slot contains the most recently used block. Okay, so that it is easier for me to understand. So I am maintaining it such that most recently used block always remains on the top. So whenever I need to replace, I'll replace just with the top block.
yes, ma'am. I understood that. My query is about out of this context actually.
Okay.
Like when we are removing the most recently used thing outside the memory, main memory.
It is removed. It is again now present in the secondary memory only. It is no longer in the primary memory.
Yes, ma'am. Then like the computation would be slower, right? Because the user is again and again going back to that particular point. Like usually, like since it's
See, this thing we will understand better once we go to week 11. Okay, so there we will see how these blocks actually move from secondary memory to main memory. So there are different transaction logs for that. Okay, different channels for that, but it is not slower. Okay, there are different processes like input output process, read write process. So these happen between, see, even inside the main memory there is this main memory buffers, and then we have transaction buffers of their own. So we will understand that better when we know what are transactions and all. Okay, but here what happens is when we are removing a block, it is no longer present in the main memory. So it has to, again, if you want to again reach out for that particular page from, you again have to bring it from the secondary memory only. So that's why the computation in the RAM itself is faster, but this transfer time is a cost we have to bear, right?
Okay, ma'am.
But this part, the explanation, I understand what you're asking. It will be way clearer when we go to week 10 and 11. Okay.
Got it, ma'am. Yeah, my doubt was like general doubt.
Okay, so these two policies are clear for everyone. Now you can find out hit ratio, I hope. Right.
Yes, ma'am.
Because this is a very important question in term point of view. LRU, MRU. Okay, so just be very familiar with this. We will practice more in our division sessions. Okay. So we have covered binary tree, binary search tree, magnetic disk, and page replacement policy. These are the main topics from which maximum number of questions will come from week 8. Other than that, what is left is in 8.1, 8.2, you will see the algorithms are there, what are the different types of linear, non-linear data structures, right? What are timing complexity? Just a bit of introduction to timing complexity, state complexity.
Ma'am, can you please summarize that what is the motto of page replacement policy?
Yeah, page replacement policy is where it originates is in the main memory buffer we have limited space. That's the thing. Okay. Main memory is very much smaller compared to the secondary memory, hard disk. So in main memory we cannot use it randomly. Okay, we have to plan the usage of the main memory or RAM. So in these assigned buffers only, we have to make sure that we bring all the desired page frames from the secondary memory. Now, since we can't bring all the page frames together, because that will probably be larger than the size of your RAM, so we have to bring them one by one, and a particular amount of memory is assigned to us, which is these main memory buffer slots. So in these slots only, we have to keep those page frames. So when we are watching a movie, what happens? Each of the page frames come and go, right? Like if I'm following least recently used, that means, let's say you watch the first 10 seconds, that is one page frame, then the second 10 seconds, then the third 10 seconds. These are filling the 3 slots of the buffer. Now you want the next 10 seconds, so now the least recently used page frame, that is the first 10 seconds, those will be removed, and in place of that the next 10 seconds will come. When you rewind, we again have to go back. Now let's say it is like this. I'm watching a movie. My first 10 seconds are there, second 10 seconds are here, third 10 seconds are here. So when I'm at this 30-second mark, I wanted to rewind back to whatever happened at 10-second mark. So what will I do? Is it a hit or a miss?
Hit.
Because that frame is still there, right? So I can
Yes.
just bring it to the top. Right. And then again, everything that follows. Okay. So
Got it.
this is the idea of why we need page replacement, but obviously it is a much bigger concept. In DBMS, we just do a part of it. Okay, because this is not core of DBMS itself. It is just to understand how data is stored in hard disk and how the transfer occurs. Okay, so in the
there could
next,
be
yeah,
n number of these buffer slots, no?
yeah, whatever buffer slots are there, that will be mentioned in your question. Okay, that we are using a main memory buffer of 3 slots or 4 slots. And we will ask you that we want you to use this LRU algorithm or MRU algorithm. Okay, and the reference will be given to you, the reference of page sequence numbers.
Ma'am, this is a
Yeah.
out of context doubt. If we are having more number of buffer slots, then the faster
Then there will be less number of misses, right? Because then we have more page frames stored. So if you want to access a certain page frame, the odds are that it is already present in the buffer, because you have more number of frames.
we
The
can
lower
reduce the latency, right, ma'am?
Yeah, we can reduce it. So when you have higher number of slots in your buffer, then the misses are going to be lesser. There will be more hits, right? But when you have lesser, if I have 2 slots, then there will be frequent misses. But there is a trade-off also. You cannot take that much memory from main memory, because it has other processes to learn as well. It has to run different processes alongside. Let's say you're watching a movie, but there are other things happening also, right? When you turn on your computer itself, the BIOS has to run. So main memory is assigned to a lot of different tasks at once. So every task is assigned some part of the memory, right? And every processing has to happen in the main memory only. Primary memory is where everything happens, and secondary memory is where you store the data that you don't want to lose once the power is shut down. Okay, now from week 8, the other part of it that I was saying, the algorithms part of it, so that can be discussed in the next class along with the practice questions, because nothing much is left in week 8, just the algorithms. But I think first 2 lectures are there. That's it. Okay, so do you have any doubt from whatever we covered in today's class? Anyone? Because see, after the class, I will be sending you the PDF of all this. I have compiled a PDF of whatever notes I have written here. I will give it to you on Discourse. Other than that, if you need any other help regarding this, you can ask me. I would suggest, yeah.
You said you would share a formula sheet. Could you share that?
Yeah, that one also. I will share the entire drive link with you. You will find everything there. Okay.
Ma'am, can you please share the link also, the Discourse link?
Where should I share the Discourse link?
Ma'am, in the chat.
No, I haven't created the post yet. I will create it and then I can share, right? No worries. See, if I make the post, I'll pin it. Okay, then you will find it on the top. And from now onwards, since now we are at the end of the course, we have the last 4 weeks are left. So these last 4 weeks are the most content heavy ones. So every week I will try to give you some notes. which are already there in my drive. So you can read those also if you think that it is helpful to you. Okay, but please do make sure you watch all the lectures also thoroughly, right? Don't just mug up all the notes and go. Also try to understand. But I will be giving a lot of formula sheets for week 9 also, week 8 also, and week 10 and 11 are purely, I mean, a lot of numerical type questions will come from there. Not numerical, but you will see those are the difficult weeks. So we have serializability, transactions. For those also, I will provide some notes to you. Okay, all of them I'll share in a single Google Drive, so you can just keep the link of that.
Where, in Discourse or where?
In Discourse, yeah.
Thank you.
If you even visit my profile now on Discourse, you can find out in my profile I have shared that all notes. There is a post called all notes. So in that you can find the drive link. Otherwise, I'll be sharing right now only. So just wait for 2 minutes. Okay, so please do join the next class on Saturday, and then I hope I will have a class with you for week 9. We'll meet again. Okay, so thank you for joining, everyone. Hope this was helpful.
Thank you, ma'am.
Thank you, ma'am.
Ma'am, just a general doubt that in quiz 2, week 1 to 8 will come, or 4 to 5?
No, 1 to 8.
1
All
to 8.
1 to 8. Yes.
Okay. Yes, there was some like announcements sort of in your file.
No, quiz 2 we usually have 1 to 8 only, but maximum weightage will come from 5 to 8.
Okay.
Okay. All right. Thank you.
Thank you so much.
Thank you, ma'am.
Ma'am, where can I find these numericals? Were they in the previous year end-term exam paper?
These came in PYQs, so you can go back for a few terms and search the in-term PYQs or the quiz 2 PYQs.
Okay.
Yeah.
Thank you, ma'am.